Alright, so in this video I'm going to go through the 2013 June Unit 1 paper. So as pretty much always, we're going to start off with some particle physics, subatomic particles stuff. We've got an atom of calcium, and it's ionized by removing 2 electrons. State the number of protons, neutrons, and electrons in the ion. So the little number at the bottom is the proton number. It tells you how many protons are in the nucleus. So that's fairly straightforward. So there are 20. Number of neutrons is going to be the nucleon number, which is the top line, minus the proton number, which gives you 28. In an atom, normally the protons and electrons balance each other out. That's why it's neutrally charged. But it says it's been ionized by removing 2 electrons, so there are going to be 18 electrons. Okay, so now it wants us to calculate the charge of the ion. So it's going to have a relative charge of +2. And we can convert that into its actual charge in coulombs like this, and that's going to be 3.20 times 10 to the minus 19 coulombs is the charge. Then it wants the specific charge. So specific charge, you should know, is the charge divided by the mass. So it's going to be the charge, which we just calculated, and divide it by the mass. So there were 48 nucleons, minus 27, and there were 18 electrons, which quite frankly is not going to make any difference to the mass, given that they're like 20,000 times smaller, but we should have it in there in the calculation because they are a part of the mass. And when we calculate this value, it ends up being 4.0 times 10 to the 6 coulombs per kilogram. And that's your final answer. That's the specific charge. Okay, so that finishes question 1. Nice and straightforward to start off with. Alright, so question 2, we're going to look at some Fineman diagrams. So we've got a positron emission, so a beta plus emission. We've got a proton turning into a neutron, and we want the Fineman diagram for, it says here, the quark interaction. So we want to look at what happens to the quarks. So to identify the particles labelled A, B, C, and D. So when a proton turns into a neutron, an up quark turns into a down quark. So that's what A is. It's a down quark. You wouldn't be able to put a neutron in there because it clearly said it wants a quark Fineman diagram. So if it's positive going in and neutral coming out, that must mean B is taking a positive charge across. So that's going to be a W plus particle. C is going to be your positron, or an E plus positron, or you can call it an anti-electron if you like, but it's typically known as a positron. And then the particle D, in fairness, C and D are interchangeable, but typically it's done this way around, is an electron neutrino. Okay, so the mark scheme may let you get away with just calling it a neutrino, but you should, as being a good physicist, be more specific. It has to be an electron type because it's a positron and an electron neutrino. That's why electron-lepton number is balanced. State the interaction responsible for this process. Well, if we have a look, we've got a decay going on, and you should know your beta decays. We've got a W plus boson, so that tells you it's a weak interaction that's responsible. It is for both of your beta decays. State which letter represents that. That was B, and that's where you see the squiggly line going across on a Fineman diagram. It shows you an exchange particle or a charge mediator, whatever you want to call it. State one difference between this exchange particle and a photon. A photon is neutral. I'm just going to write this short. And a W plus is charged, or more specifically, it's positively charged, but it's charged, and that would be the difference. You could also look at it in terms of mass. W bosons have mass, photons do not. Or you could talk about rest energy, all of those kind of things. All right, let's finish off question 2. Okay, so last question, question 2. Energy and momentum have to be conserved in this process. State 2 other processes that need to be conserved and show that they are. So baryon number has to be conserved. So let's write out the decay. This is how I always show conservation. Proton to neutron plus electron, anti-electron or positron plus electron neutrino. So we're going to look at baryon number. So we've got a baryon number of 1 going to 1 plus 0 plus 0. So you can see that's conserved. That works. 1 on to start with, 1 afterwards. Another thing that needs to be conserved is charge. So again, let's write out our equation. Hopefully you can see this already. Now we've got proton is a charge of +1, neutrons are not charged, positrons have a charge of +1, electron neutrino is a neutral, hence the name neutrino, and then so we can see that is also conserved. You could have picked electron lepton number here, because you would see that's 0 before and 0 after. Any of those general ones you could have picked, but those are the 2 easiest ones, I think. So there we go. Okay, so that finishes question 2. Let's move on. Okay, so we've got a 6-mark question for this paper. So we've got hadrons and leptons are 2 groups of particles. Write an account of how the particles are placed in one or the other of these groups, and we should include how interaction classifies them, examples, details of any similarities, and how one of the groups can be further subdivided. If you get this as a 6-mark question in your exam, the exam board is being very nice to you. This is about the easiest 6-marker I've ever seen, but we've got to answer it anyway. You can only do what's in front of you. So, first thing, how we separate hadrons and leptons. Hadrons interact through the strong interaction, leptons do not. So let's get that down. Okay, so the biggest mistake I see with this kind of thing is students get it into their head that hadrons interact through strong, leptons interact through weak. That's not true. Both types can be fermions, so both can interact through the weak. That's not how you distinguish them. Hadrons do through strong, leptons don't. Okay, and I just realized I wrote electrons. Let's fix that right now. Leptons. Okay. So that's the type of interaction, is how you classify them. An example of a hadron. Let's go for the most commonly known one. A proton. An example of a lepton. Let's go for the most commonly known one as well. And an electron. Easy stuff, like I said. So some similarities between the 2 groups. So in your category of hadrons, you've got charged and neutral particles, whereas leptons, you also have charged and neutral particles. That would be a similarity. They all have mass. That would be, or a rest energy. That would be a similarity. So that's essentially the similarities really between them. So let's get that down. Okay, so that's our similarities. Both have rest energy or mass and can interact through the electromagnetic interaction if they are charged particles. And it wants us how we can subdivide them. So let's go with the hadrons. So hadrons can be split into baryons and mesons. That's a split. Leptons in theory can be split into 1st, 2nd and 3rd generation, but that's not really part of the course, so that's not going to be what they're looking for in the answer. So hadrons are subdivided into baryons and mesons. An example of a baryon is a neutron, and an example of a meson are pions. It mentioned earlier to give examples of stuff, so since we've subdivided, we might as well give examples of those as well. So contrary to what I said earlier, actually, you should hope you don't get a question like this in the exam, because frankly, every single candidate who sits the exam should get 6 marks in this question. How can you show you're better than everyone else if you get this easy as possible question? So hope you don't get this question. It's rubbish, but let's continue on anyway so I can stop berating this question. Every type of particle has a corresponding antiparticle. Give one example of a particle and its corresponding antiparticle. There's so many ones we can give. Let's just give the first one that was discovered. So electrons were discovered ages ago, but the first antiparticle that was discovered was the positron. So let's give that one. Obviously, there's a whole range you can pick from. Most of them just put the word anti in front of it and it becomes its antiparticle. State one difference. The difference between them is the charge. So they have opposite charge. So electron is -1, positron is +1. Okay, so that completes that question. Let's move on very sharp. All right, so we're going to look at the photoelectric effect. So we've got light of a certain frequency incident on the surface of the material. Electrons have a maximum kinetic energy of 1.7 times 10 to the -18. Explain why the electrons have a range of kinetic energies up to a maximum. I swear this question came up 2 years ago, but anyway, let's just answer it again. So first of all, this is all explained using this question here. So Ke max is calculated by taking the photon energy and subtracting the work function, the minimum energy required for an electron to escape from the surface. So that's going to be the first part, essentially talking about the terms of this equation. So let's get started with that. Okay, so that's the first part of my answer. I'm running out of space, but I haven't quite finished yet. So the photon energy is constant as the frequency is fixed and energy is directly proportional to frequency. The work function, which is this term right here, it's the minimum energy to emit an electron from the surface of material, and it's also fixed, meaning using that equation, if those two are fixed, there is a fixed maximum kinetic energy. So the final point is explaining why there's a range. So electrons might be deeper in the material and so will have a smaller kinetic energy than a surface electron. That's what we have got there. So you'll have enough space for it. My handwriting is much bigger on the screen. Okay, so that's that one done there. So we've got the work function of the material. So we can calculate the photon energy, we can calculate the max Ke, and that would give us the work function. So let's rearrange this equation. So work function is the photon energy minus the maximum kinetic energy. Let's get the frequency, 3 times 10 to the 15. So we've got 6.63 times 10 to the -34. And so 3 times 10 to the 15 minus the K max, which is 1.7 times 10 to the -18. Let's dig out the old calculator and find out what the effect is in joules first. Alrighty, and we get a value of 2.89 times 10 to the -19 joules. And if we divide that by 1.6 times 10 to the -19, that would give us the number of electron volts. So we can see it's over 1, but it's between 1 and 2 essentially. So divide by 1.6 times 10 to the -19, that's all in brackets, and that gives us 1.806 yada 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 times, and that's electron volts, which is roughly 1.8 electron volts. Yay! Short-out questions are always nice because once you get there, you know you've got all of those marks, which is great. Work out the threshold frequency of the material. So Planck's constant times HF. Threshold is equal to the work function. So that means threshold frequency is 1.8. Well, let's just go straight into the joules one. So it's 2.89 times 10 to the minus 19. 6.63 times 10 to the minus 34. Or you should store that number in my calculator so I don't have to write it in all the time. Never mind. And that gives us a threshold frequency of 4.4 times 10 to the 14 hertz. There. I'm going to give it two significant figures because if we look back at the data we've been using, those are all 2 sig fig numbers, so this answer will be 2 sig figs as well. So let's finish off this question 4. State and explain the effect on the emitted electrons of decreasing the frequency but keeping the intensity constant. So if you keep the intensity constant, the rate of emission will stay the same as long as the frequency is above the threshold frequency. But decreasing the frequency decreases the photon energy, so that will decrease the kinetic energy of the electrons. So we've got two things so we're going to explain what would happen. Photoelectrons have lower kinetic energy. That's stating what would happen, and in terms of explaining it, the kinetic energy is given by photon energy minus the work function. Decreasing frequency decreases photon energy. The work function is constant, so max KE will decrease. You could probably also have talked about the fact that you might have gone below the work function or the threshold frequency, so you would now have no electrons emitted. That would have been valid as well. If you keep the intensity constant, that means the rate at which energy is supplied to the material is constant. That would actually mean you have more photons arriving per second if each photon has lower energy. So that would actually result in an increased rate of emission. So that's not quite what I said earlier, but actually now I've had a chance to think about it, we get a larger rate of emission because each photon has a smaller energy, but the total energy arriving per second is a fixed value because intensity is constant. So you could have gone with that too. So there's a few different options. Okay, so state and explain the effect on emitted electrons of doubling the intensity of radiation while keeping frequency constant. Double energy means twice as many photons incident per second, because each of the photons have the same energy, which means twice as many photo emissions per second. So state what would happen is double the rate of photo emission that looks like an E. Have I gone French? No. Double rate of photo emissions. And why? Because a good part of any explain answer is you've got the word because in it. Twice as many photons are incident per second. That is the effect of doubling the intensity of that radiation. Okay, so that finishes this question 4. Let's move on to some electricity. All right, so this question's about AC. So if you haven't got to AC yet because you're doing the new spec and that's in year 13, or that's how we do it at school anyway, do feel free to skip past this, but if you've done AC, let's continue. Okay, so we've got a sinusoidal alternating voltage and how it varies with time in milliseconds. Looks very standard. Looks like your max is about 64 approximately as your peak voltage. So your peak to peak voltage is going to be 2 times by 64, so that's what, 128 volts. State the peak voltage, well, it's half of that, so it's going to be 64. Root mean square. To get root mean square, you just divide the peak by root 2, which is 64 over root 2. So let's do that. 64 divided by root 2, 45 volts. There is your RMS. I'm guessing it's going to ask us what the frequency is, so I'm just going to pick up the time period while I'm here. So we can see the time period, or the time for 1, is 10 milliseconds. So let's see if I was right. So that's what we've got here. I've picked up that time period. Frequency is 1 over the time period, so 1 over 10 times 10 to the minus 3 is 100 hertz. So fairly straightforward there. The next part wants us to draw a line to show the DC voltage that gives the same rate of energy dissipation as the alternating. So this is what RMS is. RMS tells you the voltage or current in DC that dissipates the same power as your AC waveform. So you essentially would see a horizontal line at V is equal to 45 volts, roughly speaking, because that's what we calculated RMS was earlier. I can't draw it because this program doesn't let me flip back between pages. Bit annoying. Never mind. Okay. An oscilloscope has a screen of 8 vertical and 10 horizontal divisions. Describe how you'd use that oscilloscope to display the alternating waveform in figure 2, so you can see that 2 complete cycles are visible. So first thing is you have to connect your signal to the Y plates of your, so that's how you get a waveform at all on your oscilloscope. Plates. Those of you wondering why I decided to include that is because I couldn't figure out what the 3 marks were if we didn't put this. So that would be one of them, I think. And then what we're going to do is we're going to adjust the Timebase and to how many squares did we have in the horizontal direction? So we've got 10 divisions in the horizontal. We want 2 complete waveforms. A time period was 10 milliseconds. So we're going to need each square to be 2 milliseconds per division. That would be this precise setting you'd want it on. So you get a full you want 20 milliseconds because you want 2 time periods there. That's essentially what you're looking for. And then your peak to peak was 128. So let's see roughly what should we put that 128. We've got 8 vertical squares, and then Y gain to 16 volts per division, or maybe you've only got like a 20 setting, but that's roughly speaking you want 16 volts per division, so you can show 128 across your whole screen. So those are the points you'd need to make there. Okay, so that finishes that question. So we've got a circuit showing a battery, and we've got electromotive force is 12 volts, and we've got internal resistance 1.5. and it's connected to a 2 ohm resistor in parallel with an unknown resistor R. The current is 4.2. Show that potential difference across the internal resistance is 6.3. So that's fairly easy. We're just going to use Ohm's law. So we know the current through the internal resistance is 4.2. We know its value is 1.5. And if we multiply those together, I'm guessing we get something near 6.3. We get exactly 6.3. Well, isn't that nice? So we're just going to use Ohm's law there, and the fact that the current through the internal resistance is the current through the battery. Calculate the potential difference across the 2 ohm resistor. So the supply is 12. It's lost 6.3 across the internal resistance, which leaves behind 5.7 volts to be across the rest of the circuit. And because they're in parallel, they're both going to have 5.7 across them. So if we want the current in the 2 ohm resistor, we're just going to have a rearranged version of Ohm's law. We know the potential difference across it. We know its resistance. So this is pretty straightforward. 5.7 divided by 2 is 2.85. So I'm going to give it as 2.9 because you should be giving that to 2 sig figs there. Doing the current through R, well, we know the total current is 4.2. Total current around the circuit is 4.2. We know 2.85 of it has gone through the other resistor, so 4.2 minus that 2.85 gives us 1.35 amps. Oh, that looks like such a mess. So 1.4 there to 2 significant figures. All right, so that concludes this part. Let's continue on. I'm going to guess it's going to want us to figure out what the resistance of... There we go. So to get resistance, again using Ohm's law, this comes up a lot. We know the potential difference across is 5.7. We know the current was 1.35 when it was unrounded. So 5.7 divided by that answer gives us 4.2 ohms as the resistance. Calculate the total resistance in the circuit. So the resistance of the parallel section is 1 over 2 plus 1 over 4.2. So let's work that out. So 1 over our answer plus 1 divided by 2, 1 divided by that gives us 1.35 ohms. So the total resistance is 1.5, the internal resistance plus the 1.35 plus 1.5 gives us 2.85, so that's going to be 2.9, the right number of decimal places there. Okay, so that's finishing off that one. So on to part B. The battery converts chemical energy into electrical energy that is then dissipated in internal resistance and the 2 external resistors. Using appropriate data values that we've calculated, complete the following by calculating the rate of energy dissipation in each resistor. Because we know the potential difference, I'm going to use the P equals V squared over R method. So across the internal resistance, the potential difference was 6.3. So we square 6.3 and divide by 1.5, giving us 26.46. So that's basically 26 watts. Across the 2 ohm, it was 5.7. So 5.7 squared divided by 2 gives us 16 point blah blah blah. So 16 watts. And across R, the potential difference again was 5.7. The current through it was 5.7 squared. We figured out its resistance was 4.2 blah blah blah, giving us a power of 7.7 watts there. So we're using the potential difference across each of the components and the resistance of them. That gives us that. Show that energy is conserved in this circuit. So let's work out what the power in is. So it's the current times by the EMF. So that's 4.2 times by 12. 4.2 times 12 gives us 50.4 watts. Sum of the outputs. So if we add all of those numbers we've got together, so it's 26 plus 16 plus 7.7 gives us 49.7 watts. These are approximately the same because we've rounded values. Same. So energy conserved, because power in is equal to power out, shows that if for the same time energy in equals energy out. Alright, so that finishes that question right there. Okay, so we've got a 6-volt battery with 0 internal resistance. We've got a potential divider circuit with an LDR, a variable resistor, and a fixed resistor. For a particular light intensity, the resistance of the LDR is 50 kiloohms, the resistance of R is 55 kiloohms, and the variable resistor is 35 kiloohms. Calculate the current in the circuit. So what we're going to do is EMF divided by total resistance. So that's 6.0 divided by 50 plus 5 plus 35 times 10 to the 3, because they're all in kiloohms. Let's do that. 50 plus 5 plus 35 times 1000. 6 divided by answer gives you 6.7 times 10 to the minus 5 amps. So a pretty small current going into the circuit. Okay. Calculate the reading on the voltmeter. So we're going to use Ohm's law, specifically looking at that resistor. Okay, so we've got the current, we just calculated it, 6.66 blah 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 times 10 to the minus 5. The resistance of which across which the voltmeter is connected is the 5 ohm resistor. So let's calculate that. That gives us 0.33 volts across that one. So a very small fraction, but that's not surprising because it's much smaller than the other resistors. That kind of makes sense. State and explain what happens to the reading on the voltmeter if the intensity of light on the LDR increases. So first of all, what's going to happen? It is going to increase. That's stating what's going to happen. So what happens is the total resistance decreases. That's what happens if you increase light intensity on an LDR. Its resistance decreases, so the total resistance would decrease if one of the components decreases. We've got a fixed EMF. So current increases. So for a fixed EMF, resistance and current are inversely proportional to each other. And then just using Ohm's law, the resistance is fixed because it's just a fixed resistor. Fixed. Current increases. So V, or the voltmeter reading, increases. Okay, so that's what would happen there. Let's flip to the final part. Okay, so for a certain application, at a particular light intensity, the potential difference across R needs to be 0.75 volts, presumably to turn on some kind of light or something in response to the change. Resistance of the LDR at this intensity is 5 kiloohms. Calculate the required resistance of the variable resistor in this situation. So let's use the potential divider equation like this. We want to find out what the total resistance is so we can find out what the variable resistor is. So it's going to be, we're just basically going to swap V and RT. So the EMF we know is 6. The potential difference we want is 0.75. The resistance of the fixed resistor is 5,000. So we need the total resistance to be 40,000 ohms. Okay, and then so the resistance of the variable needs to be the total minus the fixed resistor minus the LDR. So that's going to be 30 kilo ohms at this point, and that's the variable resistance setting. Okay, so that finishes off this paper. I hope you found this video useful to clear up any issues you had. If you're not clear about anything, or you want anything clarified, or you think there's a mistake somewhere, please do comment and let me know. I'm always keen to clear those things up. But thank you very much for watching, and do look out for further videos with this kind of thing. Okay.